I want to not only focus on Earth, but also a little bit on the other terrestrial planets, just that you know, that you not wonder that not only talk about the Earth. Actually, I'm working more on other planets than Earth, so therefore I prefer a little bit to move to the other planets as well. So what is the outline of my presentation? So I want to address what you heard already today several times, I guess. From where and when does the water come in the first place to the inner solar system? And I want to address in particular the volatile loss and input during accretion and plant formation. What I'm interested in, because I'm actually doing more plant interior dynamics, so what is happening in the planet, not what is coming from outside. So I'm dealing with what is the distribution of water during the process of plant formation. So is there still some water in the interior? Is there an ocean, or when did the ocean form? And also about the early atmosphere. And so the main question for me is actually, do we start with a dry or more wet interior, yeah, of the planet, of Earth, Mars, Venus, whatever? And to start with that question, maybe you're not all familiar why water in the interior is important. I mean, you all think about water as a surface is important, but also water in the interior is important. And to explain it a little bit more in detail, with that you can imagine immediately, oops, what is this? That is too fast. That if you don't have any water in the interior, you don't have outgassing in the sense of that you produce a secondary atmosphere by water, for instance, or even carbonate or carbon. So that is one thing. Water affects extremely the solidus temperature, the melting temperature. So if you have a little bit of water in the interior, you reduce the melting temperature. In the extreme case, like this. So this is dry solidus melting temperature, and you have 0.01 weight% of water. You reduce already the solidus by 30 Kelvin. You think it's not much, but in the evolution of the planet, that can make a difference. And the more water you have, the more you reduce the melting temperature. And you can imagine that influences the volcanic activity, because then you produce more melt, and you influence the outgassing and everything what's happened at the surface. The next point is, which is also very important, that's the effect on the mantle viscosity. The mantle viscosity more or less determines the strength of convection. So if you have a low viscosity, convection can be very efficient. If you have a high viscosity, the convection is more sluggish, and also the cooling is less efficient. Yeah? The stronger convection, the stronger you can cool the planet. So what you see here is the equation of the Newtonian relation of the viscosity with the activation energy, pressure, and activation volume. But the most important point is here is this inverse proportional to the temperature. That basically means for low temperature you have a high viscosity. So what you see here, maybe I explain that first. That's the depth. This is either viscosity or temperature. So this is a temperature profile, a typical one. You have a cold surface, you have a thermal boundary layer where you increase the temperature. In the interior, more or less a constant temperature which increases with the adiabat, and then you have a lower boundary layer here. So the important thing is, at the surface with low temperature, you have extremely high viscosity. At these viscosities, nothing happens with the flow. I mean, it's really stiff. Yeah? So there's no convection. So with increase of the temperature, you decrease the viscosity. That's what you see here. And here is where convection takes place. With other words, at the surface, you have a stiff lid, and convection takes place below. That's for all planets in our solar system, like Mars, Mercury, Venus. It's not clear that much. At the moment, there is stagnant lid convection. There's only the exception, I'm sure you know that Earth has plate tectonics. So for Earth, there's something special. It's not that the other guys are kind of wrong, it's more the Earth which makes a problem. Because if you just use the assumption of the viscosity, as it is given here, you have a stiff lid at the surface, which is at the surface, and below you have convection. So you need to have some different processes to break the plate and to bring the plate down in the interior. So the point I want to make here is actually that already a little amount of water, like 100 ppm, reduces the viscosity by 2 orders, something like that. Yeah? So it's extremely little amount of water have a strong influence on the viscosity and then a strong influence on the dynamics, on everything what's going on also at the surface. So again, small amount of water has a strong influence on the interior dynamics. Therefore, people like me who are doing the interior dynamics are in particular interested how much water do we have and how is it distributed in the interior. Okay, and another point I want to address that sometimes I think is ignored. So we know, I'll come back to that later, that terrestrial planets had water and still have water also in the interior. But if you have a planet with a stagnant, and it depends then when that water came into the interior, but assuming that you start with a dry interior and you have the stagnant planet I just mentioned to you, I don't know how you want to bring the water into the interior. It just, maybe there are some processes, but at the moment we don't know. So if you start dry, bring then water, the water and the volatiles will be at the surface and the atmosphere, but not in the interior. The same is actually with the plate tectonic planets. When you say, okay, plate tectonics brings the water into the interior, but the problem is if you start dry, how you start plate tectonics? Because I have to say we don't know exactly how plate tectonics work, what we need to initiate plate tectonics, but water is definitely an important ingredient for the whole process. And some people believe if you don't have water in the interior, you can't start plate tectonics. So that can be an issue. And if we figure out now that Earth started dry, or the other planets, you have to explain how to start plate tectonics then. And also, probably you also know that today we have plate tectonics. We don't know actually when it started. Some people argue it started from the beginning, but most people think, oh no, it started something like 2.5 billion years ago. So if this is the case, you have a long period also where you probably have a dry interior, have nothing to degas, and it would significantly influence the atmosphere evolution as well. We have basically 3 accretion scenarios. I just mentioned that, starting from dry planetesimals, you have a dry interior, then you kind of form the core. Then, because we know we have water today, you have a late supply of volatile-rich planetesimals or comets or whatever, and then you have water at the surface and the atmosphere. Different scenario is that you have already accretion of dry and wet planetesimals or bodies. But the point is, and I'll come back to that later, that there is efficient processes that remove the volatiles from the interior by processes like oxidation, impact, and magma ocean degassing. I come back to that later. So if that is the case, you basically end up with more or less the same situation than is its model before. On the other hand, if one can imagine, okay, we have accretion of dry and wet material, but inefficient oxidation, degassing, and so on, that would think the starting point, whatever the starting point is, but after the planet formation, you would have some water in the interior, and then the whole process would continue. So I want to address which one of those is more likely, although I have to admit we don't know exactly how it really works. Before I start with that, I want to address the point, because what is wet and what is dry? I mean, that is certainly kind of question of definition. So if we look at Ganymede, it has 50% of weight percent of ice and water fraction in comparison to the rock here, so we would say that is wet. But also for the Earth, we say it is wet in comparison to Mars, right? But because we have a surface ocean. But on the other hand, if you put that surface ocean into the interior, you end up with 300 ppm of water in the interior. That's more or less nothing, right? I probably would say that. And we don't know exactly how much water we have actually in the interior. There are estimates from, well, in addition to the surface ocean, from 0.5 to 5 ocean masses in the interior. There's some estimates even going higher, but approximately like that. So you end up with still not a large amount of water in the interior. So you can argue now, is that wet or is it dry? As I said, it's kind of a definition, how to define that. And for instance, just to have an imagination what it means with the ocean. So if you bring the ocean into the atmosphere, so not degas, what is it? Vaporize the ocean, you have 270 bar of atmosphere. So you know, we have at the moment we have 1 bar of atmosphere. So in that sense, it's a lot of water, right? Because you have very dense atmosphere. To bring that in comparison to the other terrestrial planets, here I have an example for Mars, because there we know more than, for instance, in comparison to Venus. We know there is an indication that there has been surface water. Yeah, we don't know exactly how long it was stable there, but we know there was surface water in the past. And, I put it here in question mark, we know also from several indications that we had a kind of a wet interior. Wet now is what is wet. But these 100 ppm is kind of close if you put everything in the ocean into the Earth's interior. So there is no big difference actually from the water content from Mars to Earth in the relative. I mean, if you degas it, you don't get a big surface ocean because just Mars is much smaller. But in relative values, it's more or less similar. At least it looks like. Actually, we know that now from the Moon. There are also indications that we have probably a wet interior where the wet again is in that range here. That there is inhomogeneous distribution of water. When I say water reservoir, again, I mean only a little bit of water. But if you remember, that strongly influences the melting temperature and the rheology of the interior. So this is already a lot. So and therefore, the difference between wet and dry, you always have to define that, what you really mean with that. Okay, having said that, I come back to the points how do we start with the terrestrial planets? When you see the water content as a function of distance from the sun. So we heard that earlier, all material closer to the sun, when that accrete forms there at that location, they are dry. So they have more, not very much water. There are ancetite chondrites, where they believe it formed at that distance. They're a little bit more. Then we have ordinary chondrites, carbonaceous chondrites, and the comets, where they have a lot of water. And when you see, difficult to see here, but the Earth's water content is in between here. So people thought, because we know Earth formed in that place here, you should start dry, right? If Earth forms at that position and all the material which is from that place, you should have a dry, more or less dry composition. So there was the idea then, okay, Earth formed, was dry, and later there was some volatile-rich body like a comet hitting the Earth and bringing the water to the surface of the Earth. The problem, and we heard that already, is there are some constraints from the deuterium to hydrogen ratio. So this is the Earth value. And when you compare that with the comets, there was just one where it fitted, and people said, oh, that probably the water is coming from the comet. But unfortunately, we have now a new data point from the Rosetta mission that has even a higher DH ratio. So at the moment, it looks like that comet, if they play a role, they play a minor role in bringing water to the Earth or to the inner solar system. So the idea now is that the water is coming more from the asteroid belt or from chondritic material. And that also, what is this? Oh, okay. So then we come, I don't want to repeat all that stuff, but I have the impression, maybe someone can say whether I'm wrong or not, that at the moment the accretion models more suggest a mixing of dry and wet material. Yeah? Here is an example of that Grand Tech model where you bring volatiles into the inner solar system. There are obviously other models as well. But in general, one probably can say that a mixture of dry and wet seems to be a more realistic case. And this is actually confirmed now because in well, some years ago from the geochemistry that actually all the constraints, not from models but from really sample, comes from geochemistry. And at that time, well, I don't know, 10 years ago or even less, people thought, okay, we had a dry accretion, yeah, and the water supply was later. Since a couple of years, there are several papers around where they argue, no, the isotopes also show that water was much earlier in the solar system. So taking that now for granted, but I think it's still an open issue, but taking that now as a good indication, we assume now that we had an accretion of dry and volatile rich planetesimals, which doesn't solve the problem at all. Well, not doesn't solve, but we still have the issue that we have two scenarios left. So you have a dry and wet accretion. So in principle, you could have a wet interior. But we have these very efficient mechanism to remove all the volatiles, yeah, by oxidation, impact, and magma ocean degassing. So is this more realistic or is this more realistic? I want to go into more detail. What are the processes here? And you see, it's really difficult to get to this point because these can be very, very efficient of removing all the volatiles into the atmosphere. Not losing them from the whole system, but having them in the atmosphere. So again, well, it's kind of the same what I just said. So we have the processes that determine the amount of volatiles is first from the accretion. Yeah, what kind of material is coming, but that is not the end of the story because during the process of accretion, a lot of things happening, and all these that happen very early are very catastrophic in removing or in losing the volatiles from the interior, not from the planet, but from the interior. And in addition to that, I'm coming to this here, we have also later on secondary volcanism. If you remember, I told you that when you have produce melt and you have water in the interior, you have outgassing and then you have secondary volcanism. And what you also can have is recycling of volatiles by tectonics. That would be then plate tectonics. Okay, so the first process is actually oxidation. Assume that the planet forms. You have silicate material, you have iron and so on, and you have water. So before core formation, you have free iron. That free iron likes water. So it reacts with water and it produces H2 and FeO. So FeO is more than a silicate material. So H2 would outgas, so then you have a reducing atmosphere actually. At the end, you would have an oxide interior, but no core formation. You have a problem actually when you produce a planet like this and have a lot of water. So you would probably not get a core if that process works perfect. So and here, when you have a core, what you outgas then is more H2O and CO2. So it's a different process. So the oxidation phase during core formation is extremely efficient in removing water, yeah, by producing H2 and O goes to the iron. So that is more or less this point here. So that we know now that Earth and the other terrestrial planet has a core. That was also always an argument for this dry accretion. That means if there was water, we have a problem because we wouldn't have a core, right? But we know we have a core, so there must be either there was no water at the time, but we think is probably not realistic. So there may be other ways of making that oxidation process less efficient. And there is some work on at high temperature and pressure, which shows that in that case, iron moves to go into a metallic phase rather than to get oxidized. So that's at least one possibility to eliminate very efficient oxidation. And what's also, I think, is important, the core formation process itself, assuming you have a magma ocean, you have iron that is heavier, sinks down, produces a metal pond, and then like iron drops sink down. And these iron blobs, which sink very rapidly into the interior to form the core, they're also very inefficient in oxidizing, yeah? Because they are big, and the oxidation only takes place in the outer part here. So that's also an efficient way of not oxidizing all the water. Yeah, so these are two, maybe there are more, but there are at least two mechanisms to reduce that process of the oxidation, first to form a core and have at the same time water in the interior. Again, the next thing, which is also kind of bad for the water in the interior, is the volatile loss during impacts. Assume that the planet is growing and the planetesimals hit the surface, that's a lot of energy, then more or less devolatilize the whole interior. There's a work here by, what is that, Tubucci, can't really pronounce that, from 2001, where they estimated that you have complete volatilization when the radius of the target, either Mars as a small body or Earth, whatever, is larger than 1,400 to 2,000 kilometers. All the other hitting bodies, they lose all the water. So that means you have basically a wet interior, but a dry outer layers. That also would mean that smaller bodies like Mars, they would have more water, right? Because they're smaller, they could all retain their water. So there is now, is it coming here? Oh, okay, that would basically argue that we have a decrease of water content towards the surface. Yeah? Because the bigger the planet gets, you have more energy when you hit the surface and all the water goes into the atmosphere. So there is now a very recent work, because I think there is at the moment no really good idea how to keep the water. If that is true, what I've shown you before, certainly the interior of the planet would be more or less dry, yeah? Because only the smaller inner part could keep some water. But there's some new experiment, it's actually from this year, where they show that the impactor derived water resides in two reservoirs, that's in the impact melt, and in some of the in some projectile. Oh, okay, in some material of the projectile. So, and they estimated from the experiment that 30% of the water can still remain in the interior. So that would argue for that by growing terrestrial planets that may trap some of the water as they grow. And before it was more or less really difficult to understand why there still be water in the interior. We had first the oxidation, right? Then we have this impact, which devolatilizes a lot of water. That both looks like there is some hope that we keep some water. But now we have the next process, which also get rid of a lot of water, and that is by magma ocean crystallization and outgassing. I think someone asked this question before. So what you see here is the temperature as a function of radius. As I said, when the planet is growing, the more energy gets released when you hit the body. So what you typically have is a accretion temperature profile which increases toward the surface, and that would be now the surface condition, which is probably then colder. And when you look at the melting temperature is pressure dependent, at the surface is lower, increases with depth. So what you produce then is close to the surface a magma ocean where you totally melt the silicates. So what does it mean now if you have these kind of magma oceans at the surface? So what happens when you have a magma ocean? So what you see here is as a function of radius and the temperature. So you start with a, let's say, deep magma ocean. This is the adiabat, means it's the temperature in the magma ocean. So the planet is cooling now. And what you see here, you start crystallizing because as I said before, the melting temperature here is the liquidus when everything is molten. Solidus is when you start melting, and in between you have partial melt. But what you see here is that you touch the melting temperature at the base of the magma ocean. So you start crystallizing from the bottom. So, and these, typically these crystals are heavier, sink down to the surface, not to the surface, to the bottom. And you have kind of an freezing or formation of the solid material from the bottom. Yeah? Or the magma ocean decreases, so you go this way up. And all the surface here is, or the surface material is totally molten, because all the crystals sink down. Then the interesting thing is with this process that the first solids, or what you see here, the solid and the solid plus liquid, and here it is totally liquid. But the interesting point is that we have an enrichment in iron because the melt gets enriched in iron because the iron doesn't go in the solid material. And this is an unstable situation. We can see that here. Yeah. So this is the radius and this is the density. So before the overturn, it means when the magma ocean crystallizes, the density is increasing toward the surface. So here's a different phase, different minerals that formed. But you see at the surface you have a more iron-rich and more dense material, which you can imagine, which is unstable. Having heavy stuff close to the surface and lighter stuff at the bottom, that material will sink. If it is possible to sink, if you have a low viscosity and you can bring that stuff down. But that's typically what we assume that can happen. So with other words, this heavy stuff sinks down and ends basically at the base of the magma ocean or wherever it started to crystallize. And closer to the surface, we have less dense material. So that also, in addition to that, tells you that the first crust, which we probably have on the terrestrial planets, I come back later, and the moon is a bit different, it's kind of an iron-rich crust. Whether that sticks there or sinks down depends on a lot of little tiny details. I want to go into that, but in principle that would be the first crust which forms on the planet. And if you have that sinking down, that is also kind of a vigorous process where you produce during that overturn another much more melt, and then you would have at the surface kind of a partial melting of that material here. Here's a case for Mars, where it's similar, where at the surface you have an iron-rich, we would produce an iron-rich crust. More interesting is probably the moon, just for completion. Yeah, you see that? In the case of the moon, because it's smaller and because of its composition of the magma ocean, it's interesting because also first you produce dense crystals that sink down. When you crystallize the magma ocean by approximately 80%, and the crystals you've produced then at that time, that is plagioclase, which rises up, which is lighter. So in the moon, you have, what we see today actually on the moon, is this anorthositic crust consisting of plagioclase, which is at the surface, and the magma ocean crystallizes then from the bottom in between. And for that reason also, I didn't mention it before, but the process of crystallizing from the bottom to the surface is in the order of a few million years. It depends also on the atmosphere, how thick the atmosphere is and so on, but in principle it's very fast. In the case of the moon, because you produce this crust here, it insulates the interior, and the cooling process and the crystallization time of the magma ocean is much slower. It's more on the order of 100 million years. So it's a big difference. Okay, but why is that all important for our question about the volatiles? So what we have seen before is, okay, we gave a density profile which is unstable. And what is it all about with outgassing and with water? So similar to iron, which enriches into the melt and crystallizes at the end, it's the same with the volatiles, yeah, or with the radioactive elements. So if you start crystallizing silicates, they take a lot of, not a lot, only a little bit of heat source, of radioactive heat sources, and also a little bit of volatiles, of water. That's because the partition coefficient is very small. So if you have melt, start crystallizing, only a tiny bit goes into the solid part, the rest goes into the stays in the liquid part. And okay, because we effectively, it has a low viscosity, it's extremely strongly convecting, it cools very efficient. And the volatiles, because they continuously enrich towards the surface, I come back to later to explain in more detail, they get released. Yeah? But again, one point here, we start with a homogeneous distribution of volatiles, yeah? Before solidification. You start crystallizing. Then we have this partitioning of water. I don't want to explain this figure more. I think it's easier just by visualization. So you start crystallizing. A little bit of water goes into the crystals, and what you see here is then the profile here of the volatile, which is in the solid material. So, and the further you get close to the surface, the melt is more strongly enriched in volatiles. So then, with other words, that means the rocks you form later, they also contain then more volatiles, yeah? Because there is a partition coefficient between the silicate and the liquid. And whether you have a peak here depends on the minerals you crystallize. They have different partition coefficients. So for the lower material here, the partition coefficient is very small. They have an increase. There's, I don't know, probably it's garnet which is crystallizing here, which can get more water. Then you have to again a decrease, and here you have increase of water in the solid part. Yeah? You see that? So more or less nothing in the lower mantle, but you enrich the liquidus, no, not the liquidus, the liquid with water, and then you crystallize more enriched solids also toward the surface. But this is also not the end of the story. But we, well, let's put it this way. So when you have then the overturn, as I told you before, the iron-rich material is closer to surface because it's unstable, but this material has also more water. You bring that water-rich material closer to the, well, at the bottom of the mantle. Yeah? So that means after this overturn, you have a water-rich lower mantle and a mantle which has less volatiles in the closer to the surface. But now comes the problem. That is, maybe you have heard about that already, that we have water storage in the mantle, which depends on the mineralogy. And at the moment it looks like that the upper mantle can store more water than the lower mantle. So to explain you what is lower mantle, upper mantle, here's a sketch of the Earth. This is the core. This is the so-called lower mantle. And here we have the phase transition at the depth of 670 kilometers. And there we have this so-called transition zone where we have changes of the minerals. So at a certain pressure and temperature, they change their crystal structure. And while they change their crystal structure, they have different capabilities of taking the water, basically. And here we have the upper mantle, whereas Olivine, where the capacity of keeping water is, as I said before, is higher than it is in the lower mantle. So the lower mantle has more or less no possibility to keep the water. The situation for Mars is a little bit different because it has is smaller. And if you take a look where the phase transition is here, it's close to the core mantle boundary. So the region, the so-called transition zone, where you in principle can store a lot of water, is for Mars in the lower mantle. So in case of Mars, you can store a lot of water in the lower mantle. In the case of Earth, you have this small transition zone here, but the lower mantle is more or less dry. So the problem with that water storage you can have, what water storage basically means, if you have more water than that, that water doesn't go into the crystals and rise up, it's there as free water. So if you remember now, during the crystallization process, you have the upper mantle has a lot of water, but that stuff sinks down. So while it's sinking down, the lower mantle doesn't want that water, can't keep that water. So during that process, you basically dewater your material. Yeah? So that is basically the barrier here. So with other words, you can't really bring all the water down as it's indicated here. Oops, looks strange. Can you leave? Okay. It looks a bit stranger because it's different material mixed, yeah, when it's sinking down. Looks like artist view here. But in principle, it tells you that the lower mantle has more or less no water, and you accumulate most of the water close to the surface in the rocks. Yeah? Okay, that's again shown here, that the final configuration is that first you have a density decrease with radius, yeah, because you bring the no density increase? Increase should it be? No, it's wrong. Oh, it's radius, okay, sorry. So density increases toward the center, and we have a water enrichment into the upper mantle. Okay, so we know now that some water is in the closer to the surface, yeah, due to that process. But this is still not a lot of water because the partition coefficient, it was not good to see in these figures here, but the partition coefficient is very small. So in principle, there's not much water there. So there must be kind of a mechanism to store more water in the rocks, and this is possible if you consider the whole process of magma ocean crystallization in more detail. So what you see here is here that's the core mantle boundary. This is the front where you have everything solidified. In that region here, you have crystals, but a little bit of melt. The rheology here is dominated from the solid material. On top of that, you have a little bit of crystals, but it's more like liquid, it's fluid, so it's convecting very vigorously. And here, everything is liquid. So when the planet is cooling, this front, the solidification front, moves upward, the same as this rheology front is moving upward. So the trick now is that during that cooling, melt can be trapped in that region here. And that is easy to imagine, that when the planet is cooling, it is very fast cooling, you more or less can trap melt in that region here, and it is not squeezed out. Yeah? But if the cooling would be slow, that melt could rise up and you would have no or less melt in that region here. So with other words, it means the faster the cooling rate, the more melt remains in the interior. And what we see from magma ocean crystallization models, that the cooling rate is extremely fast. So they even models argue that you can trap a lot of melt here, which means, if you remember, water is in the melt. So that means you can more or less trap not just melt, but also volatiles in the interior of the planet. Is that somehow clear? Yeah, so that's a mechanism again. Degassing by crystallization is very efficient, but this is a way to keep some water in the interior. So in their estimates, how much volatiles or how much melt can be still in the interior, and there's some estimate from 1 to 10% of melt can stay there, and then you can calculate, depending on the partition coefficient, how much melt is then, not how much melt, how much volatiles are still in the interior. So, but again, from the overturn and all these processes is now the question, how is the water distributed? And if you remember that it can be more close to the surface, but it can be also during continuous convection, it can be kind of mixed, it can be more homogeneous. That is an open issue, how that melt is distributed, how that water is distributed. And typically people assume that we have a homogeneous distribution of volatiles, but I think the next step would would be to look into more details where really that the water-rich material is in the interior of the planets. For instance, for Mars, as I mentioned, the lower mantle in principle can store a lot of volatiles in comparison to Earth, where we have this small transition zone where you can store more water. And that can also influence strongly the dynamics of the interior. Okay, now we come to the atmosphere. What we've seen now was so far that we enrich the melt with water, which then is outgassed to the atmosphere. But how does it outgas? And that strongly depends on the atmospheric pressure, actually. So what you see here is the percent of water which remains in the melt or in basalt at the end, and this is pressure. So we see here this curvature for CO2 and H2 and also sulfur. So the big comparison or the big difference here is for CO2, even for high pressure, the melt doesn't like to stay in the liquid phase, so it degasses. Different it is for water. Only for low pressure it degasses more or less immediately, but for high pressure water likes to stay in the liquid phase or in the rocky phase. So that means for the evolution of the atmosphere, that's what we see here. So that's the outgassing pressure as a function of time for a specific model now. But what you nicely see here, so take this line here, that's the CO2 outgassing, and that is the H2 outgassing. So first CO2 goes into the atmosphere, yeah, for more or less a long time. Because you have a high pressure and the water can't get out. Yeah? But as the magma ocean is crystallizing, you continuously enrich water into the melt. Yeah? So with time, yeah, because the crystals sink down, and the magma ocean at the end has a thickness, let's say, 10 kilometers. So at that time now, you have so much water in the liquid part that it becomes that the saturation level is higher and material can get out. Yeah, is that clear? So you more or less enrich water in the liquid part, and at a certain saturation level, because you enrich it, it can outgas. So and at the end of the evolution, when the magma ocean has totally crystallized, you have, for this specific model, you have even more water in the atmosphere than CO2. So CO2 is more or less almost outgassed. Here it's a little bit more, but for H2O, you have at the early start you have no outgassing at all, and at the end you have a strong degassing of water. And how that looks like depends in detail on how much CO2 and water you have in the interior, but it's a typical evolution of outgassing of a magma ocean. Yeah? Okay, so the story with the early atmosphere is, however, much more complicated, as you can imagine. So we first have to look at that we can capture and accumulate gases from the planetary nebula that I haven't mentioned so far. But what I did was that we have a release of H2 during the oxidation of iron. So the first atmosphere you produce is kind of a reducing atmosphere. We have this impact volatilization, I've mentioned that, yeah, so that you can't really store water in the interior, but what you do is you release it to the atmosphere, so you produce atmosphere by that process. And we have, in particular, this catastrophic outgassing due to the magma ocean solidification. And later in time, you have degassing by secondary volcanism. That is all the process to produce the atmosphere, but the life is much more complicated because you have a lot of processes to lose the atmosphere by some process, by thermal loss process, by UV radiation, or by non-thermal loss process, sputtering, ion loss, photodissociation, and so on. Also by impacts, and for instance on Earth we form carbonates, so basically all the CO2 that got into the atmosphere is kind of washed out into the carbonate. Whereas if you release all the carbonates we have at the moment on Earth, you produce an atmosphere like on Venus. Yeah? So Earth is just lucky that it could store all the carbonates, no, all the CO2 in the carbonates. And we have some absorption and regulate. So if the story I want to make here is, if you really want to study the atmosphere, I was just talking about how to outgas, yeah, from all these processes. But really to understand all these issues, when and where, what kind of atmosphere you have to look that in much more detail. Yeah? And I can't do that because it's just not my topic, but that's something interesting to look at. Yeah? And people do that to see, to compare losses and input of the atmosphere as a function of time. Okay, just to summarize at this point, what happens with the water during accretion. I think that's the main topic of my presentation here. It's first, we had this oxidation, you remember? So we have efficient oxidation before and during core formation, because water reacts with the free iron. And you release basically H2 into the atmosphere. But the good thing is for the water in the interior that there are processes which kind of make these oxidation process more inefficient. That's, for instance, when you have large iron blobs that sink into the core, then there can't be that the reaction. So that's one way to keep water in the interior. So the next thing was the impact devolatilization. So basically, when you have the impacts, you lose all the volatiles. So you have a decrease of the water content towards the surface. So smaller bodies have more luck, they would keep more water. But there is now a new experiments that show that approximately 30% of the volatiles can be stored in impact melt and in the breccias. That was the word I was missing before. And at the end we have this magma ocean solidification. So we just described, we have efficient outgassing first of CO2 and later of H2O, just because water is more saturated in melt, and it can later, when you continuously increase the water content in the melt, it can later degas as well. And to keep, again, water in the interior, what I'm interested in is that first we have the partitioning of volatiles into crystals, which is at least already a small amount, but it's not sufficient. But an efficient way is that we trap melt during the rapid process of solidification, and that keeps also melt plus volatiles in the interior. So all these three are, again, very efficient in removing the volatiles, but there is some hope because they're all not totally efficient, so we can keep some. And as I said before, we talk about few hundred ppm of water in the interior, what we need, which is not that much. So I think these processes can get a lot of stuff out of the interior, but still keep kind of a critical amount in the interior to proceed with plate tectonics and these kind of things. And to explain why stagnant planets have melt in the interior. As I said before, if the volatiles come very late, and the planet was formed already, has a stagnant lid, I don't think there is a good way of bringing it back into later in the interior, right? There is no plate tectonics, there is no mechanism to do that. So there's the only way that these processes are not that efficient as they could be, in principle. Okay, so here I have some take-home messages. So as I said, I mean, one can probably argue about that, but at the moment it looks like we have an accretion of dry and water-rich planetesimals. So we start with kind of a mixture of both. We have a strong devolatilization of the interior in the early evolution of these effects processes I mentioned already. I didn't mention that, but the denser the early atmosphere, because it also keeps water in the interior, remember? The higher the pressure, the more water can be stored in the liquid phase. So the denser the early atmosphere and the faster the solidification, because in that case you can store trapped melt, the more water can remain in the interior. But we talk about ppm level. We don't talk about really a lot of stuff. Okay, and that would be this scenario then, the third one I've shown before. Okay, one thing from the simple consideration we just met is that the early atmosphere probably changed from a more reducing condition to a more oxidizing condition. That the reducing here comes from the core formation process because we release H2. And the more oxidized condition, if you the volatiles you release during the magma ocean process and so on, seems to be more on the oxidized condition. Okay, and if we had a global magma ocean and fractional crystallization, what we can more or less expect, we probably have an inhomogeneous distribution of volatiles. First, we have an increase toward the surface after solidification, remember, because you enrich volatiles in the liquid. Then also, when you crystallize, there are more volatiles in the solid part. But we have a remixing of water during this so-called magma ocean overturn because dense stuff sinks down. And what's happening during that process is at the moment difficult to say because no one has really modeled that. But there are several possibilities. And there, what's probably important is that we have potential storages. In the case of Earth and Venus, it's in the transition zone, which is close to the surface at depths of 500 to 700 kilometers. In the case of Mars, it would be the deep mantle, because there you can store more water. But what is also possible that due to convection and all these processes, it's more or less homogeneously distributed. So that's an open issue. So we can recycle volatiles in the case of plate tectonics. But again, if you start really dry, we have a problem of the initiation of plate tectonics. In general, it's an open issue because we don't know exactly when it has started. If we look for the other planets like Mars, Mercury, I haven't included here Venus because for Venus we don't know whether it probably had early plate tectonics or kind of a mechanism like this. But for Mars and Mercury, it's more or less clear there is just one way of outgassing, yeah? Because you only can, due to volcanic activity and these other processes, you outgas the interior, but there is more or less no way of bringing it back into the interior because they are stagnated planets. And one point I've also addressed is that the very early crust, due to crystallization of the magma ocean, is very iron-rich. But what happens after that with the overturn and so on is very open. And when you start producing continental crust, probably some of you are interested in that, really then depends when plate tectonics really had started. Yeah? Or whether there are other processes of also to generate kind of continental crust. And from these early crusts being iron-rich, there's in particular one exception, that's the Moon, because it produces these plagioclase crusts, which is a totally different composition. And for Mercury, people start also thinking of a different crust now. I think they talk about carbon-rich crust. It's a similar process that at a certain time, when you have the crystallization of the magma ocean, at a certain time, crystals are produced that are lighter and rise up. Yeah, so that's a possibility also for Mercury, but that we don't know. But for Mars and for Earth, I think it's pretty sure that such a crust doesn't, this plagioclase crust doesn't exist or never exist, and we would probably start with more an iron-rich crust. And with that, I'm done. I'm too fast, huh? No?
Perfectly.
Perfect, okay.